Good morning. So the project I'm going to present on today focuses on, or has its roots in a bit of a wild concept. What we want to do is we want to try to combine medium voltage power electronics and medium voltage cables. We want to try to combine this into a single structure that you could integrate together. So the power electronics can be integrated directly into the end of the medium voltage cable and allow us to kind of combine low voltage and medium voltage cables together. Now this is more than just an integration project. We're after more than just a high density form factor. This is a very neat package, this idea of a cylindrical power converter that's the same aspect ratio and form factor of the cable. It's a nice image, but at its core we're trying to do more than just accomplish a form factor and more than just get a high density solution. We actually want to try to learn from the way medium voltage cables are manufactured. Learn from the way they're manufactured and try and inherit some of their benefits. Things like passive cooling. What if we could get rid of all the cooling systems associated with these medium voltage and medium power converters? What if we could get better voltage scaling on these? So what if all we had to do to increase the voltage of a power converter was increase its diameter, just like we have to do with a cable? Dr. Chung Lee in his tutorial session yesterday discussed a little bit about the complexities of scaling the voltage level like that when he talked about the transformer, how the whole problem changes when you try to increase the voltage. What if all we had to do was increase the diameter? Dr. Singh, our keynote this morning, talked about manufacturing and how the manufacturing people love it when you can omit steps. What if we could build power converters the way we build a cable? Raw material goes in one side, finished product comes out the other via extrusion process. If that sounds too good to be true to you, that's okay, I agree. That's quite a lofty goal. I was thinking yesterday during Dr. Ming Shu's presentation when he talked about building a power converter that takes up no space. I was wondering which one of us had the more lofty goal. But if you could do this, you end up with a power converter solution that could go anywhere a cable could go. We could go underground, we could go above ground, we could go underwater. Anywhere you've got space for a cable, now you've got space for a power electronics solution. The idea being that this basically forms like an intelligent splice. Now we can splice low voltage into medium voltage, we can splice DC into AC, and have it all handled directly in the cable. So what I want to do today is take the next 15 to 20 minutes and talk a little bit about some of the considerations for doing this. Some of you may be thinking, you know, the power converters I build could never fit in that form factor. You might be right. There's quite a bit of constraints to work around, and so what I'd like to do is talk about a couple of those constraints, what we need to do, what we need to compromise on in order to get into a form factor like this, and what benefits we can get as a result. Before we get to that, I want to talk about kind of the lens that I want to view this through. When we talk about kind of the design workflow, if you will, for power electronics, a lot of us would start with kind of the application level requirements. Let's talk voltage, power, efficiency, that sort of stuff. We'll develop a circuit, select a circuit, learn from the literature, find a topology we like, and then we'll lay it out on the board. I think a better approach for something like this, when you're talking about such a radical evolution of the integration strategy, is to flip the process around a little bit. So let's start from the integration problem. Start from the integration and work backwards to the topology. I think this is critical because the benefits of the cable are so tightly coupled to its structure. As soon as I put a trace that runs from the center of the cable to the outside of the cable, I've destroyed the coaxial structure, I've destroyed my voltage scaling properties. We're so sensitive to that. So I want to hold on to that structure, I want to protect it, and I want to preserve it throughout the design process. Let the topology fall out of that. If you can do this well enough, eventually you can extend the idea to your application as well. Maybe what we find out is this doesn't apply to every application, but maybe there's a subset of those that aren't affected by the constraints, but that are heavily benefited with the advantages. So that's the idea. So I'll get started talking about thermal a little bit. And the thermal problem really boils down to a single parameter, loss per length. So how much loss can I evacuate for a given meter of length of this system? The higher power I have, the more loss I have, the more length I need. And this parameter is driven primarily by the environment. So we're able to take all the environmental conditions and basically boil it down to the one axis, the y-axis in this case. And these contours then represent different like power levels, for instance. So let's say I had let me get my pointer here. Let's say I had a converter that was directly buried in the soil. For a direct buried environment, we can get somewhere between 200 and 300 watts per meter. So for a 250 kilowatt system, we need something like 15 meters of length. In another environment, say on the vented cable vault, if we were lower in the spectrum, that same 250 kilowatt converter might need to be over 100 meters long in order to evacuate the heat. And that's an environmental limit. We can't really get around it. So this has implications for the topology, and what it means is it's not all about density. So my highest loss components are my switches and my inductors, and we may be inclined to take those and pack them together as closely as we can and get a very dense form factor. If I need to operate in a certain environment that requires a low loss per length, it doesn't matter how dense that is, I still need to stretch it out over 100 meters, and so that density didn't really benefit you. And so what naturally falls out of this is a modular structure where we need to be able to distribute these heat loads along the length of the cable, however long that needs to be. And once we distribute them, this sort of modular nature kind of falls out of it, where we could have modular power converter cells that we stack end to end. And every time we add a cell, we increase our power, but we also increase our length. And so we kind of break that barrier. Now, in terms of environment, the environment that we selected for this was an underground cable vault. If you're not familiar with these, this is basically a concrete box under the sidewalk, and this is where the medium voltage cable splices are housed so they can be serviced and inspected. We kind of identified this as a good environment to look at for sort of early technology adapters, if you will, because it's a pre-existing space, it's an opportunity for a retrofit. But it is a difficult thermal environment to work with because it's on the lower end of the loss per length spectrum. So we did a little work on this. One of the reasons we like this environment is we've got a little bit of flexibility on the loss per length because ultimately it's just free convection into air. We know how to work with that. Basically, it boils down to two parameters: crank the surface area and crank the surface temperature. If you can do that, like with some sort of fin structure, you can greatly improve that loss per length. So this is a prototype thermal system we came up with that tries to increase the surface area by about 20x to try and increase that loss per length a little bit. And the reason we want to do that is we have a length constraint inherently with this. Some environments don't come with a length constraint. This one does. These boxes are usually 3 to 5 meters long. So you want to get significant power capability within that length requirement. You got to drive the loss per length. So we tested this system here. This tested out about 1,500 watts per meter. And if we plot that out as like power versus length, for a 3 to 5 meter box at 1,500 watts per meter, you can handle something in the high hundreds of kilowatts range, sub 1 megawatt range, assuming you're at 99% efficiency. That efficiency starts to drop off too much, and you can have that power requirement pretty quickly. But that's the order of magnitude we're looking at roughly with a thermal system like this. So one of the key, I think, takeaways here is that the distributed loss requirement, it really necessitates a modular structure. And you may have environments that you can't increase your loss per length like we did here. And so how important that modularity is kind of depends on the environment a little bit. It's something to be considered when you're doing something like this. Next, I want to talk about some more electrical considerations here. So we kind of talked about this modular structure, and we like the idea of kind of a series input, parallel output sort of structure. So with each additional cell we add, we're increasing our power and simultaneously increasing the maximum voltage that we can handle as well. So we like that structure, and we also like the idea of capacitive isolation in here as well. And I think there's other ways to do this. We like this because it fit neatly into this coaxial form factor. Like I said, we really want we want the integration in the structure to kind of drive that topology piece. And I like the capacitive isolation because you can kind of draw 3 distinct layers, if you will, within this schematic, where you've got the high voltage center conductor down at the center. You have your capacitive isolation then occurring radially with your lower voltage output side components around the circumference. So this was kind of our starting point. We liked how that fit in there. We started with it's a switch capacitor buck, which once we stack up modules like this, effectively becomes like a multi-phase switch capacitor buck. This turned out to be a bad idea as a nature of its, as a function of the topology itself. This topology works once you throw multiple phases in here. You basically have to transfer this charge from one cap to the next. You're passing this energy from one bin to the next as you move it down the length of the converter. And that causes a problem when you have these really long cells. And so when we first ran into this problem, we said, oh, no problem, we'll just shrink it up. We'll pack these components as tight as we can. We'll get that loop as tight as we can. That's how we usually deal with these inductance problems and PCB layout issues. Shrink the loop. And this was great for us because it took the whole problem and shifted it to the thermal side. We created an impossible problem for our thermal team because this became way too short. They needed way too high a loss per length in order to cool this thing. We had to stretch it out. So feasibly, if you had a really high loss per length, you might be able to do this. But if you want to generalize this to others, other loss per lengths, as this thing stretches out, your commutation loop's going to stretch out. And so this basically gives you an environmentally dependent commutation loop, if you can imagine that. If you can imagine taking your PCB and moving it to a different room and all of a sudden its commutation loop changes. That's basically the structure we have here. So we want to decouple this. And the way we did it is we modified the topology, effectively adding another capacitor in here. So now we can just pass the charge back and forth within a single cell, localize that high frequency commutation loop to one cell. This works well, but there's more to this, because one of these cells could easily be 1 meter long or 2 meters long, depending on your loss per length requirements, and now you still end up with a commutation loop on the order of 1 meter or more. So to really address this, we need to look at the packaging a little bit. So I'm going to take this commutation loop schematic here, and I'm going to start adding a little bit of structure to this. So we build the capacitors with a series of smaller capacitor cells, so all of those are paralleled up. And I'll take this and I'll kind of revolve this schematic around a central axis to create the coaxial shape. So we'll revolve this around, and what we end up with is a kind of a single switch position module in the center, nested within a larger one on the outside. So we have a coaxial module, or 2 coaxial modules, 2 coaxial capacitors, and our commutation loop is a loop in 2D, but once we revolve that loop around the axis, we effectively end up with a toroidal commutation loop, if you will, as a function of this coaxial structure. And that turns out to be very effective for keeping that commutation loop low, even as the capacitor scales and your radius scales with voltage. So here's a look at some of the hardware. So these are the 2 coaxial silicon carbide modules we built. You can see the smaller one and the larger one. These nest within each other, along with the coaxial capacitor array. So you can see the high voltage contact is here at the center. That current spreads out radially with the lower voltage contacts around the outer circumference. And when you integrate these, you find that the loop inductance is very, very low. Because of this sort of toroidal commutation loop that we have, we're able to keep the total loop inductance around 24 nanohenries. That's below 10 nanohenries per cap, which is quite low given their size. As a point of comparison, if you look at a commercial capacitor of a similar value, 5 kV, 500 nanofarad, you're looking at about 5 times larger inductance, even though that commercial cap's about half the size of ours. You can see as a function of this array, we don't have quite as high a cap density as you might, or quite as high an energy density as you might have in a rectangular form factor. So the cap has been stretched out a little bit, but despite that, we can get 5 times lower inductance out of it. Now the math says that this is going to scale really well. We've only built 1 cap. We've built 5 kV caps. We're working on 10 kV caps, and then I'll be able to tell you for sure. The math says it'll work, but come back next year and I'll tell you whether or not it worked. So the other thing I want to look at is the electric field a little bit. So this, I've kind of added some more parts to this topology here. So this is that modified topology from before with its 2 capacitors. I've gone ahead and appended the magnetics components here at the end. And what I'll do now is I'll go ahead and draw the potential map over top of this. And we can notice some coaxial patterns emerging here. We have the high voltage down here at the center. As we move out in the radius, you have the lower voltage along the outer circumference. I assure you this is not accidental. This was a result of a lot of work to try and bend this topology and work the topology to find solutions to the parasitic problems such that you can maintain the structure. As a point of comparison, I want to show you another way that we could have addressed this parasitic problem. So what we did is we added another cap in here to allow it to circulate within the cell. The other thing we could have done, which is probably more in line with current techniques, which is if your topology is set and you have a series capacitor buck and you know you're sensitive to the commutation loop, just lay it out in such a way that the commutation loop is low. And so what we've done here is we said, okay, well, let's just take 2 of those switch capacitor bucks that we started out with. Let's just take 2 of those and let's co-package them. So instead of passing the energy all the way down the chain of cells, let's just bounce it back and forth between 2. And we'll co-package those 2 to get a tight loop between each other. You can do this, but the electric field pattern is quite a bit different. You can see the dramatic change here if I can put these side by side for you. You can see the dramatic change here between the co-packaged pair of switch capacitor bucks versus this modified topology. You can see how the high voltage here makes its way all the way out to the outside and breaks this coaxial structure. So this is why it's so important to start from this side. Keep this in mind because, as I say, it's a very fragile thing, and small changes to the topology can have a big impact to this. Now, some of you might be thinking that picture here at the top doesn't look very much like a cable. In terms of its coaxial structure. It's a little bit more complicated. We expect it to be. After all, these power converters are quite a bit more complex than cables. So what's really important, really what we're looking for is that the voltages that scale in the system are coaxial. There's a number of voltages that don't scale because of this topology, like the series or parallel output topology. The voltages on the switches don't really move around very much. Even as you stack more cells, the voltage stress in the switch is constant. And so that's something we can kind of explain away. We don't need to deal with that. We can handle that the same way we'd handle any other voltage problem, because once we solve it once, we're done. Where we want to maintain the coaxial structures and the voltages where these scale, so that all we have to do is dial in that radius to scale it for a different voltage. So that's what the electric field concerns look like. So to take a quick look at some hardware, this is one of our prototype scaled cells that we have built, or one of our prototype coaxial converters. So this has both the capacitors in it, both the coaxial capacitor arrays, the two coaxial silicon carbide modules here in the center, and the magnetics appended on the end. Some other structures here that we haven't talked about yet are the heat pipes. So these copper bars that you see, these are heat pipes that go from the modules and help spread that heat out over the whole length of the system. So the length of the system here is, for this structure, is determined primarily by the capacitor. We have to have those modules down in the center to keep that commutation loop low, so we use heat pipes to help spread that heat out over the whole axis. So this is a 5 kilowatt or 50 kilowatt system at 5 kV that's limited by the caps. And right now it's limited at about 80 C, and that's a function of the capacitor technology we have, and also a function of we don't have a cooling system on it yet. But where we're headed next is a 10 kV version of this, so same power level, but we want to get to 10 kV. So this will use a custom capacitor that we're having manufactured that can handle the 10,000 volts, but can also handle the higher temperatures. So we'll have a high temp 10 kV cap in here. That's going to cause things to stretch out a little bit, and we'll also put that cooling system on that we talked about earlier. So to wrap things up, I think the goal of this work is really to explore this radically new integration strategy. It's inspired by cable construction and design, but really what we're after is not the look of a cable. We want the benefits of a cable. We want to be able to get at the voltage scaling. We want to be able to get at the passive cooling. Eventually, we'd love to get at the manufacturing as well. You can see there's still a lot of discrete components in here. We'd like to get rid of that. We'd like to move to processes that are a little bit more formative, a bit like the evolution of the transformer that Dr. Chung Lee talked about, where instead of having a hands-on process with lots of small pieces, they move to a process where they can, or like PCBs that scale very well. We'd like to take a similar approach here. Step one is to really get the power components integrated, figure that problem out. Step two is dial up the manufacturing a little bit. So the research objectives here are really to understand, how easy is this to do? What can you do, and specifically what compromises do you need to make? We all know that there's no free lunch in this business, so where do we have to pay? What's the constraint? And some of these constraints that we found are the modularity. That's really critical. I mean, lucky for us, modularity is kind of an attractive term in the business. We all love that idea. But here it kind of necessitates it. The thermal problem really necessitates that modularity so that you can distribute these heat loads over such a long distance. The coaxial structure, we found that it kind of favors these capacitively isolated structures. It fits in there very nicely. But I'm sure it's not the only way to do it. The intercell commutation is a problem, especially when you have very low loss per length and you have to stretch those commutation loops out over such large distances. So it's important to get to the bottom of that. So you're kind of constrained by things that can keep that high frequency current contained within the cell without letting it spread down the axis of the cable. And that these coaxial field patterns are very critical. It was amazing how many times during the project we made one very small change to the topology and it disrupted that electric field. So keeping that in mind and allowing that to drive the problem so that you can maintain those benefits of the cable are very, very critical. So I'm just about done talking. Before I stop, I'd like to acknowledge all the people that worked on this. I was very lucky to be the one today to share this work with all of you, but there's been a huge team behind this across various institutions, with lots of different skill sets from the material science, magnetics, topology, control, thermal, mechanical. It's quite an extensive team and a very talented team, and they've all made this possible. So thank you very much.
On? There we go. Thank you very much. That was a great presentation. Very innovative, very interesting. One of the things you mentioned was that I'm having a little bit of a hard time understanding. Maybe you elaborated on it, I just didn't catch it. But the concept of putting more in series, increasing the power level, could you explain that? Because it seems like there's an interface at that point with the interconnection on the cable. You're going from high voltage to low voltage. So how does that increase the power if I put more of these in series? Or did I completely misunderstand the architecture?
So it's a, let me get back, where's the picture I want? Right there. So the outputs are paralleled. So the understanding would be that as you add more cells, you're simultaneously increasing that input voltage and increasing the output current. So the understanding would be that you're also increasing your input voltage. Those two are kind of coupled. Conceptually, we could develop a cell that tweaks its parameters a little bit, such that, you know, as I add more cells, I keep the voltage the same and just increase the output power. But as long as we're stacking identical cells, you're kind of doing both simultaneously.
Right. So it's the parallel connection with the common high voltage line going between the different cells, if you will, correct?
No, the high voltage input is getting chopped up. So the high voltage input, that's seriesed up. So as this voltage increases, the V in for each one of these blocks is consistent. So they all see 2 kV. So when I add another cell, I have to increase the high voltage side.
Oh, I see.
bit.
Okay.
Yeah.
All right. Okay. All right. And thus the can you go down to the image where you show the there's no one else behind me, where you show the voltage versus the cable section? It was near the end. It was the heat map of voltages.
This one here?
There you go. That right there. Okay. So this is what you were talking. Okay. Because it looks like to me that, okay, I see this what you're saying. No. Okay. I guess what I'm not seeing is the interconnection between the cells.
No, we're looking at a single cell here.
Okay.
We're looking at a single cell. So this is your highest voltage coming in. You've got a voltage drop across this switch because each one's, you know, you've basically, as you stack these cells in series, their input sides, you get like a series bridge that forms.
Okay.
So you get a voltage drop across this. This voltage then becomes the highest voltage in the subsequent cell.
Okay.
Yeah.
All right, that makes sense. How much did you find the parasitic capacitance of the cable to be a factor in the design of the topology?
Significant.
Okay.
Yeah, we're still working through those problems. Yeah,
fine.
one of the requirement here from a thermal standpoint is that you need to get this heat spread out axially, but also over the whole radius, and that whole heat, the whole circumference. So you end up with a very large area you need to spread this heat out of over, which incurs a very large parasitic capacitance to ground. So we need to work through that.
The other thing I noticed is you added the extra capacitor there on the other side of the switch. And what I was thinking to myself is, okay, at some point you're switching a capacitor into a capacitor, correct? As part of the commutation.
Yeah.
You're basically through a switch.
Yep.
Did you find that you had to decouple the parasitic inductance? Did you find that you had, or did you find that the inherent resistance of the switch itself tended to DQ that coupling through the switch device?
It's not a direct. We're not putting them in parallel necessarily. So only one. So if you look at this, let me go to a cleaner schematic here. This one here. So only one of those switches is active at a time. They don't both turn on to move it over. So one of them is active at a time.
Okay. All right. All right. Thank you.
Great presentation. I have many questions, but ask one. What is EMI problem? Did you look into, or are you considering EMI issue this technology will face?
That's in progress. That's linked to the capacitance problem. We have a lot of experience switching these things very quickly here at CPES, and we know it's a serious problem. And so that's why, we've got our first system now that we're starting to run, and so we're just starting to get to the bottom of those problems. I should say we're starting those problems. Maybe not start getting to the bottom, but we're starting those problems now.
Mainly, you are putting high voltage, net at core of the conductor followed by outer, and can EMI of switching impacts your low voltage electronics, right, or circuit, and causes a lot of issues that beyond your control, right, shielding, all that you may want to do. I mean, like EMI could be a big challenge in this. That's what I'm trying to
Yes.
get at.
Yeah, we've done a lot of, I would say, higher level, kind of, if you would, preventative work on that. What makes those issues so tricky is they manifest in ways you can't predict. And so that's the part of the problem we've yet to deal with. We've done some preventative work in that and something I didn't have time to talk about today is kind of this balance between circumferential fluxes and axial fluxes. And so we play those games throughout, both in the magnetics, in the commutation loop, and the capacitance to balance where the fluxes are and make sure that things we don't want to couple, we keep those orthogonal. And so some of these components are set up to have all their flux circumferential, others are set up to have it axially, and we play those games to try and mitigate crosstalk. But I'm sure there's a number of issues that that haven't shown their head yet.
Okay, thank you.
This is Bo Xue from Delta Electronics. I'm trying to understand your application here. I see the capacitor is very important. Are you trying to use this capacitor to achieve galvanic isolation, or you need another stage to achieve a galvanic isolation? I feel this film capacitor, they cannot qualify the galvanic isolation.
It's a good question. When we started out with the idea that the isolation would have to occur further down the chain. That was one of the starting principles. As we moved on, we found that we kind of benefited from floating the grounds, if you will, having separate input and output grounds. Now, is that enough to say we've replaced the transformer? I'm not sure. That's going to take more work to really get to the bottom of whether we need additional galvanic isolation either on the input or the output to kind of meet the standards that people in this industry would expect. That's something we need to look into more.
Okay, thank you.
Just want to acknowledge, I'm Dusan Borojevic. We proposed this, when, 6 years ago to DOE, Department of Energy, Office of Science, but they thought it's too far-fetched or whatever. But ARPA-E decided to fund this 2 years ago, so I want to acknowledge again Department of Energy and specifically ARPA-E for funding this and allowing us to explore this. I would just say that we're still fighting the science more than engineering. And there is a long way to go, but it's really exploring what are the limitations and what are the possibilities, and Mark presented that nicely. Thank you.
Thank you.
Christina is leading the whole project.
Okay, let's thank Mark again. Thank you.